Hi guys, so in this video we're going to look at mistakes that mechanics students make too often in their exams or make too often in their revision or just in their studies in general in mechanics. So obviously right now it's the 17th of June 2023. We're 3 days away from the 2023 paper 3 mechanics exam for both, well, for OCR and for edexcel. So those two examples do mechanics. And if you're watching this in future years, then obviously, you know, every example you do you will do mechanics, but especially for paper 3 edexcel mechanics students coming up in a few days' time, and the OCR ones as well, where you have some mechanics in that exam too. These are some mistakes that a lot of students make that you should not be making in these exams coming up. So the first mistake that I'm going to highlight is that students too often make mistakes when they deal with SUVAT in 2 and 3D, so in 2 dimensions, 3 dimensions. So we know that, you know, these two SUVAT equations here in 1D. So if you've got, like, you know, if you're a car traveling along a road, or if you're like you're running in a straight line, then obviously you've got this equation V equals U plus AT. We've got also this one as well, S equals UT plus half AT squared. But when you deal with 2D and 3D, so like when you deal with components, the I and J and the K components in 3D as well, the equations are still the same. I mean, with this first one here, V equals U plus AT, they're still the same. Remember, I'm going to come on to this actually in a minute as well. Remember, velocity is a vector, acceleration is a vector. So that's why I've underlined these. Time is just a number, it's just a scalar number. So there's no vector, time is not a vector. So yeah, that's fine there. But this one here, the now I've just note that I've changed the letter S into a letter R. So in 2 and 3D, we normally use the letter R instead of S. R means position. It's just the letter we use in maths for the position or displacement in 2 or 3D. We normally use R instead of S, generally speaking. So yeah, we've got this equation there, but that's not quite right because we need to add also the initial position onto that. So I'm going to call that R naught. So this R naught there is the initial position. So too often I see students forget this. So when you're dealing with SUVAT in 2D or 3D, so if you've got like a problem where you've got, you know, like an initial speed of 2i minus 3j, acceleration of 7i minus 10j, and you've got to work out the position after like say 4 seconds time, too often people forget to add on this initial position. So remember, when you're dealing with SUVAT in 2D and 3D, so constant acceleration. So remember, SUVAT just means constant acceleration. So we want to use SUVAT equations when we have an acceleration which is just constant, not dependent on time. So no t involved in the acceleration formula, just constant numbers. We can use the same like S equals UT plus half AT squared equation, but we must add on this initial position. And too often students forget to do that. So why do we do that? So the reason why you have to add on this initial position is basically because of integration and differentiation. So remember, velocity is the integral of acceleration with respect to time, and displacement or position, depending on whether you're using 1D, 2D, 3D, whether you're doing a 1D, 2D, or 3D problem, is the integral of velocity with respect to time. So that's just our key mechanics facts. So if you want to get velocity v, that's the integral of acceleration with respect to time. So when you integrate, so a is just a constant. So remember, we're doing SUVAT, so that means that a is a constant. So constant acceleration. So when we integrate this, we're just gonna use normal integration. So when you integrate a number, you just times it by t, the letter that you're integrating with respect to, and then you add a plus c at the end, don't you? So remember, when you integrate without limits, you add the plus c. So what is this plus c? Well, we've got this formula here, v, so therefore v equals at plus u. Now, when t equals 0, so at the initial starting point of your journey, what we're going to get is we're going to get v is equal to a times 0 plus c. So, and what I'll actually do here, instead of writing a v there, I'm just going to say v at time 0. So the velocity at time 0, when you plug in time 0, is going to be c. And normally in SUVAT, we call that u, don't we? So in the SUVAT letters, S, U, V, A, T, we call that u. So that's what this c is. So the c there is the initial speed. So the velocity after t seconds is a times t, and then plus your initial speed. So that's actually where the formula comes from. So at plus u. And it's the same thing with this equation here. So your displacement is the integral of velocity with respect to time. And remember, the formula for velocity is u plus at. So this exactly the same as this back here. So integrating this, we're going to get ut and then plus, so integrating the t, we're going to add 1 to the power, divide by the new power, and then plus c at the end there. So that's going to be ut plus half at squared plus c. Again, what is this what is this plus c? Well, this plus c is the initial position, because if we substitute in t equals 0 into the equation s equals this and this and this, we're going to get that the initial position, I'll call this s bracket 0, so the initial position is going to be u times by 0 plus a half times a times by 0 squared plus c. That's just 0, that's just 0. So you're going to get the initial position equals c. So therefore, c is again this initial position. So initial position. So when we deal with SUVAT in one dimension, we don't worry really about having this plus c there, because if you think about, I mean, let's just say you're walking along a road, like common sense just tells you it's just easier to say that your initial position is 0. So imagine like you're walking along a road, right? There's no reason why you would say, oh, this initial position there is 10. It's just easier with these one-dimensional, normal, straightforward SUVAT questions to say, okay, initial position, I'll call this IP for initial position, equals 0. So the C there is 0. So when we deal with 1D SUVAT, so one-dimensional SUVAT without any I and J and K vectors, we don't worry about having this plus C there. But when we deal with vectors, the initial position is important. Because again, if you're moving in a straight line, obviously, again, there's no reason why you would say your initial position is 10 or minus 50. Like, it's just easier to call your initial position 0 if you're doing normal, straightforward SUVAT. But when you're dealing with 2D and also 3D as well, when you've got the K vector as well, your initial position does matter. So you'll get questions which say, okay, so your initial position when you start the journey is minus 7i plus 3j, right? So this could be, minus 7 there, plus 3 there. So your initial position is going to be minus 7i plus 3j. So that initial position is important. So the position t seconds later is going to be exactly what we had back here. So this here. So your position t seconds later is going to be this this formula here. So where this r0 is your initial position. So I'm just going to put a box around that because that's really important. So this is equal to your position t seconds later. So position of your particle t seconds later. Okay, so well, yeah, t seconds. Let me just put the word in later there. So t seconds later. So t seconds after the start of the motion. So that's really important. Don't forget this initial position in your SUVAT equation in 2D and 3D when you're dealing with the I and J vectors. Okay, second mistake that a lot of students make is forgetting that acceleration is a vector. So acceleration is a vector. So if you're dealing with 1D mechanics, so straightforward SUVAT, remember you can have positive or negative accelerations. Magnitude of acceleration is a scalar, so a number bigger than 0. So remember, a scalar just means a number, a straightforward number bigger than or equal to 0. So let's just remind ourselves of the difference between scalars and vectors. So distance is a scalar. Like you can't have negative distances. You know the distance traveled that you travel on a journey it's a number, right? It's a straightforward number bigger than 0. But displacement and position, these are vectors. So your displacement in one dimension can be a negative number. So relative to where you started, you can have a negative displacement. If you're dealing with the 2D vectors, so I and J vectors and that kind of stuff with 2D SUVAT, then again your position is a vector. So it depends on where you are on the grid, so the XY axis basically. So again, you can imagine like an XY axis, that's your Y axis, that's your X axis. Your position is obviously a vector on that XY axis, and same with 3D as well when you've got the K vector too. Again, same with speed. So again, speed is the magnitude of velocity. So let me just make a note of this here. So speed is the magnitude of velocity. And remember, when you want to get the magnitude of something, and again, distance as well, is the magnitude of position. So let's just make this clear as well, magnitude of position. So the modulus of position is what distance is, and the modulus of velocity is what speed is. So remember Pythagoras. You use Pythagoras to get your speed, which is again a scalar. You can't have a negative speed. It's a number bigger than or equal to 0. Velocity, a vector on the 2D axes or on the 3D axes if you're using the k vector as well. And again, magnitude of acceleration. Again, this is a scalar, so it's a number bigger than or equal to 0. So it's the modulus of your acceleration vector. So it's the modulus of your acceleration vector. And acceleration, again, just this term acceleration, that is a vector. And obviously time is a scalar, like you can't have a vector of time, at least in A-level maths. So time is just a scalar number bigger than or equal to 0. Yeah. Okay, so the third mistake the students make is not drawing force diagrams, or not completing force diagrams, not adding every force possible on a force diagram. So really do practice your force diagrams, getting all your forces on your diagram. So let's have a go with this one. So I mean, let's say that we've got like a block there. I'm going to call the mass of this block there M, and I'm going to call the mass of this block here like capital M. So obviously you've got weight going downwards. So weight is always vertically downwards, down on your page. You've also got the weight there, mg, and we assume that the weight goes from the center of mass. That's kind of how you assume what you have to assume with this question. So you've got the two weights there. What else do we have? So we've got a rough plane, so there's going to be friction. I'm just going to assume that the capital M is bigger than the M. So basically this weight there, this block in free fall has a bigger weight than this M there. So the friction is going to be going down opposite the motion. So the motion is going to be going round like this direction. So friction is always opposite to the direction of motion. So you're going to have friction going down there. So friction. I'll just call it fric for friction. So you've got friction parallel to the slope, opposite the slope. What else do you have? So you've also got your reaction force as well. So don't forget your reaction force, your normal reaction force, I should say. So this is your normal reaction force. Don't forget that. What else do you have? I mean, you've also got the internal force of tension as well. So remember, you've got tension pulling you upwards. So I'm going to use blue for internal forces. When I say internal, the tension doesn't affect the overall motion of the entire diagram, but the tension is internal inside the string. So we've also got the tension forces acting in the direction, pulling the small block forwards, and also counteracting the weight of the big block trying to go downwards. So that's what we've got there. Don't forget as well, we've got the component of weight parallel to the slope. So don't forget this component as well. So we've got obviously the normal reaction force, which is going to be equal to, so remember we got an angle, let's just say the angle there's theta, you got theta there. Remember that this force there, so if you draw like a right angle triangle, that's your theta there. This side is adjacent to the theta, so that's going to be cos, so mg cos theta. And then the opposite component of this weight is going to be mg, so going down this way parallel to the slope is going to be mg sine theta. So don't forget this component of weight parallel to the slope, especially if you're doing an F equals ma calculation. You don't want to forget that. So those would be our forces. I mean, you've also got as well the reaction force acting from the pulley onto the string. So you've got like a reaction force there. Or you can think about it like the force acting on the pulley. You've kind of got like a magnitude of force acting on the pulley. I actually did a video earlier on that today, how you actually work that out. So do check that video out. Sorry, do check that video out, because I go through how you calculate this reaction force here acting on the pulley. But I mean, we don't really need to add this on the diagram because it doesn't, generally speaking, you don't normally get questions on that. But in case you were to get a question, we do have a reaction. We do have a force acting on the pulley and a reaction force from the pulley or acting onto the string. So do be aware of that as well. But those are all the forces in this diagram that we would need to worry about. Let's try another example as well. So let's say we've got like a rod this time. So let's say we've got like a rod which is attached to a wall, a rough wall. So there's friction in the wall. So again, rough means friction. Let's say we've got a string pulling it upwards. So what I'm going to say is you've got, a tension pulling it upwards. You've got this force of tension. We've got a mass in the center, a mass in the rod, so bang in the middle of the rod. Let's just say that we've got a mass. Let's just say that the rod has a mass of m. So your weight there is going to be mg in the center of mass. Let's say that this m is a pretty big force, so the rod wants to fall downwards. So your friction is going to act in the opposite direction of the motion. So your friction is going to act on this point there on the rod is going to act in this direction there. So again, you've got friction acting at this position opposite to the direction of motion, because the rod, because this mass is really big and this weight's really big, we're going to assume that the rod wants to fall down. And if you think about this rod here, I mean, if you've got a string pulling a rod upwards like that with a big mass, in order for this rod to be in equilibrium, you're going to need the friction to go upwards in this direction there to counteract the weight of the rod, basically. So your friction plus your tension is going to be equal to your mg. That's kind of how this diagram would work there. So you've got friction. We've also got the normal reaction force as well. So again, don't forget this normal reaction force. You've got this perpendicular reaction force, normal reaction force. So don't forget that as well. So those would be the forces on this diagram. So tension, the weight, the reaction force, and the friction too. So make sure you do get some good practice drawing these diagrams, getting your forces in. Yeah, do practice that, because those are really important. We don't want to forget any important forces when we do these calculations, especially these F equals ma calculations and these moment calculations as well, especially when we've got rods. So when we've got like hanging rods, you want to think moments as well. So don't forget your formula for moments. So remember, moment is equal to force times by perpendicular distance. So remember that a moment of a force is the force itself times the perpendicular distance away from the point in which you're taking the moment. So don't forget that formula as well. And it's really key that the distance is perpendicular to the direction of the force. That's really important. Okay, so let's go to the next slide here. So the fourth mistake that students make too much is this. So sometimes students they make a force into a component. So you can take components of forces, but you cannot make a force into a component. So let me try and explain what I mean by that. So let's just say we've got like this rod here. So you've got like a rough surface, you've got this rod attached to the ground, and it's leaning on, let's say, a wall here. So let's say we've got a wall there. So that's a wall. And you've got this like, or could be like a ladder. Like, let's just say you've got like a ladder leaning against a wall on a rough surface. You've got friction pushing, trying to stop the ladder from like slipping. So you got the friction going against the slipping, I guess the propensity for the rods or the ladder to want to slip to the left. You've got the friction counteracting that. Now let's study this friction. Let's think about this friction force. So if you wanted to, if you really wanted to, you could take components of this friction force. So obviously friction is a force. So when I say you can take components of forces, so you're allowed to do this. So you're allowed to say, okay, let's make a right angle triangle. Our friction is the hypotenuse. And then we've got this component, well, these two components like this. So you've got a component of the friction to go, going down there. So you've got, I'll call this component F1. And then you've got a component of the friction going in this direction, F2, and you've got a right angle triangle there. So that's fine. If you want to do that, if you feel that helps your calculation, that's fine. But sometimes students do this. So sometimes students say, okay, well, let's make let's say that friction is in this direction. And then I'm going to make a right angle triangle like this. And then I'm going to say, okay, well, we've got this like new force going in this direction here. So we've got the friction here. I'm then going to create a right angle triangle like this. You've got kind of something like this. We got like a force going up there, friction there. And then you've got this this kind of diagonal component going like this. I mean, this is not correct. So again, you can take components of forces. So you can basically take your force to be the hypotenuse of right angle triangle. That's okay. You're allowed to do that. So basically draw your force, make a triangle, make a right angle triangle with that force as the hypotenuse. That's okay. But you can't just like take your force and then make any random right angle triangle you like and say, oh well, we've got this special force here. I'll call this force A, for example, and this force B. Like that's not right. So you can break a force into components with that force as your hypotenuse, but you can't use this force here to make a random right angle triangle where this is like the adjacent or the opposite side. That's not correct. So just be aware you can't do that kind of stuff. So the next point number 5. So this is another thing that students struggle with, or students make mistakes with. So why is friction less than or equal to mu? So obviously normally we just use the formula friction equals mu times r, but technically it's less than or equal to. So why is that? So let's imagine we got this block here and it's on a rough surface. And what I'm going to do is I'm going to push the block to the right with a tiny force. So I'm going to call this a tiny So tiny force. So this is number one. So number one, I'm going to push it with a tiny force, and I'm going to call that force T. So a tiny force. Now, basically, the friction. Let's just say the friction is. I mean, let's just call this tiny force here like 1 Newton. Okay. Now, let's say the friction. So let's say the friction, or the maximum friction, I should say. So let's say the maximum friction. So the mu. So friction equals mu times r. The maximum friction. Let's just say that that is equal to 10 newtons. Okay, so you've got a maximum friction 10 newtons. Now, if you push the block to the right, so imagine you're going to use your fingers, you're going to push the block to the right with a tiny force of 1 Newton. Is the block going to move? No, no, it's not going to move. So what is the frictional force that you do? So when you push the block to the right by 1 Newton, is the friction 10 newtons? No, the friction is not 10 newtons. The friction will mirror the force that you push it with. Because remember, the maximum friction is 10 newtons, but the frictional force that's going to go against the 1 Newton tiny force is going to be 1 Newton. Because if it was 10 newtons, so if your friction was 10 newtons when you push this tiny force, like the block would go to the left, obviously that's not possible. If you're going to push the block to the right a little bit by 1 Newton, and that's smaller than this 10 newtons maximum friction, the block's not going to move. So your friction mirrors the force that you push it with if you push it with a tiny force. Now let's push it with the force exactly equal to max friction. So max friction. So I'm going to call this F now. So we're going to push it with a force of F. So this time F is going to be 10 newtons. So I'm going to push it with 10 newtons. What will the friction be to counteract that? So again, it's going to be 10 newtons. So the force to counteract that is the same as the driving force, is going to be 10 newtons, because that is the maximum friction. So if you push it with 10 newtons of force, the maximum friction on the surface is 10 newtons. The block is not going to move because 10 take away 10 is 0. Your resultant force is 0. We call this limiting equilibrium. So you'll see in questions sometimes, the block is in limiting equilibrium, or the system is in limiting equilibrium. That's what that means. So it means that when all the forces going to the right are equal to the so the force that you push it with to the right is equal to the frictional force, that's called limiting equilibrium. So again, with the tiny force, we're going to push it with a tiny force of 1 Newton to the right. The block will not move, and the friction will mirror that tiny force. It will be 1 Newton. Because obviously, if the friction in the tiny force, if we push it with the tiny force in situation number 1, if the friction was 10 newtons, the block would move left. Obviously, again, that's impossible. We're then going to push the block a little bit harder, 10 newtons, but that's the same as the maximum friction, so we still don't move. So I'm going to put here in brackets, don't move in situation number 1. And again, in situation number 2, the block doesn't move, so we don't move. Now, if we push it by a big force, so big force, let's say 20 newtons now. So what's going to happen? Now the block moves to the right. So the maximum friction in the surface is 10 newtons. So the friction is not going to magically increase to 20 newtons now. The friction is at its maximum. It's always 10 newtons. So then the block is now going to move to the right. So move to the right. So MTR, I'm just using that as move to the right. The block will now move to the right because your force is greater than your maximum friction. So basically what I'm trying to explain is that the friction in your diagram will always be less than or equal to your maximum friction, mu r, and mu r is equal to your maximum friction. So again, in situation number 1, the friction mirrors the force that you push it with. It's not equal again to 10 newtons, because if it was, it would go to the left. Can't do that. It mirrors, so the friction mirrors your force until you get to the maximum friction, until you push the block right with your maximum friction. And then once you push it with a harder force, a bigger force than 10, then it moves, but your friction is still 10. It hits that, it hits that kind of upper bound of 10. Once the friction's hit 10, it doesn't get bigger than 10. So that's kind of why the less than or equal to sign there is there in the first place. And remember this term, limiting equilibrium. So that's when your driving force is equal to your frictional force. It's still in equilibrium, but it literally is on the verge of not being in equilibrium. So that's why it's called limiting equilibrium. 6th mistake that people make is the difference between reaction force and normal reaction force. So this is one that I even to this day sometimes I make mistakes with. So the difference between a reaction force and a normal reaction force. So normal reaction force is this is probably the easiest one to think about. Normal, obviously we know in pure maths what a normal line is. So a line which is normal to a line is a line that's perpendicular. A normal reaction force is perpendicular. So so if you've got like a rod here and a string pulling us upwards, we've got like some tension there. So you've got a rod acting on this, attached to this the rough wall there. You've got a string pulling upwards. You're going to have a reaction force here, and this is your normal reaction force. So I'll call this NR, perpendicular to the wall. Normal reaction forces are always perpendicular. They always make a right angle with your surface. Now, the difference between a normal reaction force or a reaction force. Now, you may see in the questions magnitude of a reaction force. Again, that's the same thing as a reaction force. So I'm going to go to the next slide to go through this. So what I've just done with this diagram on the left-hand side here is I've just rotated it around so the rough wall is on the bottom of the diagram like this. So we've got a rod like this. We've got a normal reaction perpendicular. So again, this is perpendicular. And we've got friction going downwards, trying to counteract sorry, I've done this is wrong. Sorry, I've made a mistake here. Sorry, let me rub this out. Let me just rub this out. Sorry, 1 second. Right, friction is going in the other direction. Sorry, friction should be going in this direction there. So your friction is counteracting the desire for the rod to fall down. So the rod wants to go down, your friction is counteracting that. So let me just do this instead. I'm gonna rub out the arrow there, and let me do this. You got your friction there. So you got your normal reaction force going perpendicular to the wall. You got your friction going to the left. So what I'm going to do is just kind of redraw this here. So you got your normal reaction there. You got your friction again, which is a vector. Forces are vectors. So your friction's going there. What do you have if you join up this into a right angle triangle? Well, now you've got your reaction force there. So this brown force is your reaction force, or your magnitude of your reaction force. And how do you work that out? That's Pythagoras. So your reaction force is equal to so reaction force is equal to the square root of your normal force squared plus your friction force squared. So that's the difference between a reaction force or a magnitude of a reaction force and a normal reaction force. So normal reaction force is always perpendicular. A reaction force is your magnitude. So if you get a question which says to you, is the reaction force always perpendicular? Well, a reaction force is only perpendicular to your surface if there's no friction. But a normal reaction force is always perpendicular because, again, the word normal in maths means perpendicular. So just be aware of that. That's a really key one. And then the last point, so students forget their trig identity. So they think it's mechanics. I don't need to worry about my trig identities. So they forget their double angle formulas. So these ones are really important, especially in projectiles questions. Don't forget these double angle formulas. So sine 2 theta, cos 2 theta. These, well, 4 formulas in total. I mean, obviously with cos, you've got 3 different equations there. And all of them you do need to be aware of. Don't forget those, especially in your projectiles questions where you're dealing with, remember, with your 2D projectiles, you're looking at the horizontal component of the projectile and the vertical component with an angle of theta. So you do get a lot of proof questions or show that questions where you've got to show that results are true involving double angles. So if you forget your double angle formulas, you're not going to be doing very well in those questions. Don't forget those double angle formulas. Bear them in mind, especially with your projectiles questions. They're really important. So those are 7 mistakes that I think a lot of mechanics students, a lot of A-level math students make in their mechanics exams and their preparation for their mechanics exams. So do be aware of those 7 points. Hopefully that was useful. Any questions, do leave them in the comments below. And yeah, again, good luck with all your revision for all your exams, and good luck with all of your studies.